Good morning, everybody. Today, we will begin our discussion on work and energy. So we will still continue, remind ourselves the topic we discussed last time, which is potential, and to see that how is potential related to the new topic, work and energy. So we'll start with the electric potential. Let me share my screen. So recall that we have talked about V, the electric potential or voltage, which is defined, it's a scalar defined to be reference point to a location R, E dot into dl. So given an E field, you can compute your V and you have to define your reference point. Given a charge distribution, you can also find V, which is rho R prime d tau prime over script R. So how is, what does this mean? What does potential mean? What kind of information can we draw from potential? If we think about a tiny test charge, little q, and move it from point A to point B. You move it from point A to B. So let's say you have an external field and there's an external field in the space. And this little q is going to feel a Coulomb force from the field, right? Let's say that the field is in this direction, for example. Now, this Coulomb force is going to be F Coulomb. It's going to be Q times E, right? And if you move it from A to B with a constant velocity, you have an external force. Otherwise, it's just going to accelerate from A to B because it's under the electric field. So which means this external force, F external, must also be equal to magnitude, which is QE, but the opposite direction of your QE, the Coulomb force. So let's calculate the work done by the external force. The work that you have done by moving the charge from A to B is from A to B, F times dl. This is your work, right? And your F is negative QE, right? Because it's in the opposite direction of E dot into dl. So I replaced F external with QE from A to B. Now by looking at this, you realize it's the Q times negative from A to B E dl. Okay, so the latter, based on the definition, is going to be the electric potential difference between point A and point B. So the work done by the external force is equal to Q times the potential difference between point A and point B, which is V at point B minus V at point A. So by looking at this, we realize the voltage will come into place when you talk about work or energy, right? Potential carries information about the electric potential energy stored in space. In other words, it also tells you how much work is needed if you were to change the potential energy of the charge. So voltage carries information about the topic we're going to discuss today, which is work energy. So previously we had drawn the little diagram, right, to show the relationship between rho and V and E that help us. So it's like a concept map, help us memorize what's going on and organize their knowledge. So we can do the same thing to look at potential and energy. So I'm gonna put E here and V, the potential here. I'm gonna put force here and energy or potential energy here using U or PE to represent this potential energy. Depending on if you're now in mechanics, we usually just say PE as in potential energy. Here we usually use U to represent potential energy. So let's look at the relationship between each one of them. Okay, so from E to F, what is the relationship? From E to F, force is Q times E, right? Q, the charge times the electric field. And so E as to F is the similar relationship to V as to the potential energy. So from V to U, U is what? Q times V, right? Q times V is energy. Also, if you go from E to V, the gradient of V, negative, is E, right? So from force to potential energy, what is the relationship? F is equal to negative the gradient of your potential energy. Okay, so you can see that how V is to U is the same as E is to F. If that helps you to remember the relationship between these different quantities. Okay, so that's just a little sort of a reorganization of the knowledge we talked about. So if you were to present yourself with some charge distribution, if you have two different charges, Q1 and Q2, right? Then the potential energy stored in that configuration is K Q1, Q2 over the distance between them. Let's call it R. You can think about it this way. For example, you can think of, okay, well, if I have only Q1, then Q1 created an electric field around it. If anywhere around Q1 in space, you have some kind of electric potential. So at the location of distance R away, the electric potential is KQ1 over R, right? KQ over R is the potential due to a point charge. So now if you bring a little Q2 in this potential, this Q2 is going to actually Q1 and Q2 is going to have some energy stored in them. So that energy is going to be Q2 times what is the potential at the location, so V. So you got Q2 K Q1 over R, which is K Q1 Q2 over R. Right, so this kind of energy belongs to the entire system. Just like for gravitational energy, potential energy, we always emphasize in our intro physics, that kind of energy belongs to the Earth and the object. Because without the Earth, you do not have the energy. You cannot have the potential energy without the field. Likewise here, without the electric field generated by Q1, Q2 would not have such a potential energy. So you cannot say Q2 has this energy. The energy belongs to Q1 and Q2, the entire system. So, and you can also view it totally in the opposite view by saying the potential the potential generated by Q2 and Q1 is you bring Q1 into the picture later. So kind of reverse this process. So potential energy due to a charge distribution, a two discrete charge distribution is K Q1 Q2 over R. So now let's take a look at a couple clicker questions to help us better understand this particular concept. So here I present you with three identical charges. They sit on the corner of the triangle with the A on each side. If you release the top charge, the bottom two still fixed. What is the kinetic energy, the final kinetic energy of the top charge? Okay. All right, so I will let you take a screenshot of the picture and I will send you to the breakout room. So take about couple minutes on this question. Another 15 seconds. So if you haven't voted already, please put in your vote. Okay, let's take a look. Here's our results. C got the majority of the vote. B also got quite a bit of a vote. And there's next is D. So you can see that they're all similar in terms of format. At least we know how to calculate the potential energy given a pair of charge. Now it's just really how do you convert that to kinetic energy? So it's asking about the final kinetic energy of the top charge. Can anybody tell us what is the method that you use to calculate it?
Conservation of energy.
Conservation of energy. Okay, so we say that the kinetic energy is coming from the potential energy that's been stored in the first place. Okay, so how do we decide how much potential energy there is?
The potential energy from the two fixed particles.
I can't really hear. The voice is very low.
So the potential energy of the two fixed particles?
Thank you, Diego. The potential energy of the two sets of the particles. So, okay, so if you're looking at, so there are three sets, right? One pair is energy stored between these two and these two, right? And also these two. Now each of them is 1 over 4 pi epsilon naught Q1 times Q2, so Q squared over distance, that's A. Now each of them is the same. So there are three sets. How much of that becomes the final kinetic energy of the top charge?
We assume that all of the potential got converted into kinetic.
All of them. So would that be D then? Sebastian, you said all of them?
You're making me think. Just give me a second here. Yes.
Yes, all of them from where this one is involved in. Yes, all of the potential energy which this positive Q is involved in, which is this one and this one. Okay, so it's two of these. There is a third pair that's still stored in place because the other two are fixed, right? The another one kq squared over r, another kq squared over r is still stored between the bottom two charges. That one is not given to the top charge. The top charge only got energy from here and here. So it's gonna be 2 of the kq over r squared. So it's C, okay? C is correct. All right, now let's look at a different question. It's the same setup. We will release all of them. We will not keep the bottom two fixed. We release all of them. So what do you think the answer is now? Again, I'll let you discuss, but maybe for only 1.5 minutes, 1 minute or so, because you already know the question, okay? Release all of them. Okay, a few more seconds for last minute vote. Any last minute vote? Okay, I'm going to close the poll and then we can take a look. This is our results. So if we release all three, the question is asking what would again, the same question, the final kinetic energy of the top charge. So how do we do this now?
You would treat it not as, your perspective would change from the single particle, but to the entire system. And you would calculate using the conservation of energy, what your final and initial potential, what your initial energy and what your final energy would be.
Okay, so what is the initial energy are the electric potential energy stored in the system. Very good. So what would that be?
It would be 3U, which is 3K Q squared over A.
Okay. Sorry, A. And the final energy being?
Again, we assume that E initial is equal to E final. So that is your final energy.
Final energy of the system, right?
Correct, yeah.
Okay, and the system consists of three charges. So final energy of the system, which is all kinetic, right? Kinetic energy of the three Qs, right?
Mm-hmm.
Yes, so the kinetic energy of the three Qs is going to be this. And the question is asking, what is the kinetic energy of the top charge? Not the entire system, but just one of them. So what do you think the kinetic energy of the 1Q would be?
If all of them were, again, released?
Yeah.
It would be that divided by 3. So
right.
Just KQ squared over A.
Right, so that's 3 of the KQ of 1Q, right? Because they're all identical. Yes, so it is 3Q squared over A, but it's equally going to be equally distributed among the 3 of them. Each of them will have some kinetic energy. So you divide it by 3. One of them is going to have just KQ squared over R. Okay, so that's A is correct answer here. How about this question? We talked about how the potential, they obey the superposition principle very nicely, right? V1 plus V2, you add them like scalars, electric field, obey superposition like vectors, you can use a vector addition. How about system energy? If you have one system that stores energy 1, excuse me, the second system with energy 2, if we have both of them together, what I end up with 1 plus 2, W1 plus W2. I will let you discuss this. If you feel like you couldn't decide, it will be a good idea to actually think about a concrete example. Say, pretend I have this system and then I have this system. And then I bring it together. Do I get simply a superposition for the entire 2 system put together? Okay. Again, a few minutes to discuss on this one. Oops, sorry, I just hit stop share. I'm gonna bring up my share again. Okay. Are there any last minute vote? Okay, so I got everyone. Let's take a look. This is our results. Thus the system energy superposed. So I'm wondering if you used, within your group, have you discussed using a concrete example? So how did you end up with the answer that you choose? Anybody would like to talk about how they got it?
Sure. We said no, because say you had a one particle system and you're any system with like 3 particles or something.
Okay.
No potential or whatever. And the other one has some, and when you combine them, it changes the original. So you've added 0 to something and gotten something bigger.
Oh, okay. So 2 systems, one of them is just a point charge by itself, right?
Yeah.
Okay. And what is the other system?
Anything with any number of particles.
Oh, okay. So 2 maybe?
That'd work.
So this one will eventually have
0.
This one has K, Q2, Q3 over R. Okay, and then you bring them together, right?
Yes.
Okay, and then when you bring them together, what does it become? What does it look like?
It'll look like our 3 charge system above.
Ah, okay, so this kind of distribution. Okay, so this one is obviously not going to be 0 plus K, Q2, Q3 over R, right?
Yes.
Okay, so that, did I get your idea correctly? That's what you're trying to say?
Yeah, that's what I was trying to say.
Okay, yes, very good. I would say I would actually, the one is tricky. There is some kind of difficulty with ENM's theory of talking about the one, but here we're talking about the, I want to be a little bit more specific. When you're talking about the energy, we're talking about the energy to assemble the charges to the configuration. This charge is already made, they're already there. What we're doing is simply bring them piece by piece and putting them together. That's all we're doing. And that's the energy we're looking at. So you can see that, yes, Q2 and Q3 have some potential energy, but when you bring it together with Q1, right, then you need to consider the 2 new pairs by 1 and 2 and 1 and 3. So you end up with more energy than just each of them separately. Now you can use another example by saying a 2 system 1 with Q1 and Q2. I'm just gonna call all of them Q so that's easier, with a distance D between them, or a system, another system, it looks exactly the same, right? Each of them will have KQ squared over D. But when you bring them together, you can see that you need to consider this one with 1 charges, 2 charges, another charge, this one with these 2 charges, and this one with this charge. So you have multiple pairs. So it's no longer simply W1 plus W2. Okay, so W total is not W1 plus W2, because during the process, when you bring them together, you can see you are bringing it into an existing electric field. You have to bring some extra work, you have to do some extra work. If they're all positive, you can see you have done work to overcome that positive charges repel each other. You have to overcome that Coulomb force. So you have put in positive work into your system. That work translates to this extra potential energy. It's just like when you squeeze in a spring, right? Or you try to stretch a rubber band or something. You have done work, and that work goes to increase the potential energy of the system. With the spring, it's that work going to increase the potential energy, the elastic potential energy stored in the spring. In this case, that work going to the potential energy stored, electric potential energy stored in the system. So it is not just simply superposed, as in W1 and W2. So how do we calculate how much work is needed given a charge distribution. We usually follow this method of bring the charges in one by one. So I'm going to show you, there are some derivations I want to do, show you how we're going to bring the charges one at a time, starting from scratch. So let's say, so what we're trying to do now is we wanted to derive a general formula for calculating the energy stored within a charge distribution, however many charges we are given. So we wanted to build up any kind of given charge distribution. So we start with just Q, one of them, and we bring them in one at a time. And we're trying to figure out the total work. That total work is going to be the energy stored in the system. Okay, so let's bring in Q1. So if Q1 is the first charge you bring in, and there was no charge in the space, there was no electric field in the space, there was no electric potential in space. So you do not need to do any work for bringing the Q1. Since there is no other Qs, it requires no work. Now let's bring another charge in, bringing Q2. Now Q2 will be under the electric potential generated by Q1. So the work done by bringing Q2 is Q2 times potential. So potential is caused by Q1, just getting V by Q1, okay? So we can draw this little configuration. Let's say Q1 is in place here. And as some kind of position R1, and then you bring Q2 in, it is located as R2. So the separation is from your source to your field. So you bring Q2 to a point of interest in space, and you're interested in the potential at this point. So this potential is caused by Q1, so source to the field. Your R is this direction. So curly R, 1, 2. Okay, so my V2, V by Q1 is going to be K Q1 over R12. Okay, so W2 becomes K Q1 Q2 over R12. So that is the work I need. Now let's bring in Q3. So bring one at a time, the third one. So W3 is Q3 times potential. So the potential has to be by what charge or charges? So W3 is Q3 times V by, is it by 1 or by 2? Or both? What do you think?
Would it be by both of them?
Yeah, that's what I'm thinking.
By both of them. Thank you, Jasmine. Also, thank you for the answers. Okay, so it's going to be by 1 and 2 because both of these create the electric potential in space, and Q3 is going to feel it. Yes, so it's going to be Q3 times potential Q caused by one of them. Okay, so let me draw the little diagram here. So Q1 generates potential in space at the point of interest of Q3. Let me put it a little bit above this diagram. Q1 was here, Q2 was here. Now let's say Q3 is here. So the potential generated by Q1 at the point of interest, you have a distance R13. So, and Q2 is going to have a distance R23. So this notation is going to be KQ1 R13, KQ2 R23. Okay, so potential superposed, right? You simply add them up. And the work you need to do is going to be K Q1 Q3 R13 plus K Q2 Q3 over R23. Okay. So I'm only gonna do 3 and then I'll generalize it to multiple ones. So the total work is the work that you have done in 3 steps. W1 plus W2 plus W3. 1 is 0, so it becomes 2 plus 3, so it becomes K. Q1, Q2 R12 plus K. Q1, Q3 R13 and K Q2, Q3 R23. So that is the total work required to assemble the charges in this configuration. So they end up to be looking like this. 1 is here, 2 is here, 3 is here. These charges already made, all we are doing is assemble them. So that's the work required. And then that is also the energy stored in the system. So now let's extend it to any number, random numbers. So we wanted to extend it to any kind of numbers. You probably have noticed, right? We probably need some kind of I and J. So 1, 2, 1, 3, 2, 3 is kind of QI, QJ over RIJ. But we gotta be a little bit careful how we count it. We don't want to count the charge itself, right? We don't want to count Q1, Q1, Q2, Q2, or Q3, Q3. So that gives us one limitation we have to configure, constraint we want to put on this configuration is that I is not equal to J. We don't want to count those self energies. The second thing we wanted to be careful. So we don't want to count these. Another thing we don't want to count is, okay, what if we do a Q1, Q2, but then we also do Q2, Q1. Do we double count by doing Q1, Q2 and Q2, Q1?
No.
Yeah, so we don't want that. But when we do a summation, it's kind of unavoidable. So we can do that simply by divided by 2. We count everything twice and then we divide it by 2. So, okay, and then divide by 1/2. Okay, so having these 2 constraints, let's see if we can write a general expression for our W's. The W of any charge system is going to be K, or you can write 1/4πε0. The sum of I from 1 to any number, J is from 1 to any given number, but J does not equal to I. QI, QJ over RIJ. And you count it twice now, right? So divided by 2. If you didn't double count it, you also divide by 2. So now this one will give you the correct expression. Okay, so that is a general expression we have derived for any charge configuration that's already, that we want to configure in a certain way. Now, what we're going to do further, this is one of our expressions. I wanted to derive another expression. These expressions is given to us in the sort of a discrete charge distribution. I want to be able to find an expression that if I have a continuous charge distribution that I need to do integrals, I should still be able to do that. So now let's continue. So this expression, I'm going to rearrange it a little bit. I'm gonna put QI in front and you have another sum that's Q of J. sort of, I'm going to put K here. So you can see this term in the parentheses is really a potential term, right? So this is the potential of all the other charges, the potential at point I due to all the other charges at other points. There are points at J and they're not equal to I. So this is a little charge I, and it's under a electric potential in space that is created by all the other charges, so that we can view it that way. So we are rewriting our system to be 1/2 sum of I to n Qi, and there's the potential at the location of I, where I is. So if we write it this way, you can see it's relatively easy now to change it from a summation to an integral. So now let's do that. If the charge is smeared, right? So you get a charge density instead of a charge, individual charge. So our system energy is going to be 1/2. So Q becomes dQ, the integral of dQ. And V is now a function of space, right? V sub R. And dQ becomes rho d tau. So where are all these energy located? The energy is stored in the E fields. So a lot of times we wanted to be able to calculate it given the E field. So let's continue to work on this. We're not there yet. We want to be able to change our variables using the E fields because this energy is stored in the E fields. But you can see these kind of quantities that are related to our E. So we are able to connect this to the E field. So how is density related to E field? We know Coulomb's law, Gauss's law, divergence of E is rho over epsilon naught. So we can use rho is equal to epsilon naught times divergence of E to replace that quantity, right? So the system, again, becomes 1/2 epsilon naught. I'm gonna put that in front. The divergence of E times V times d tau. Okay. So at this point, I need to use a mass relationship. So I'm just gonna tell you what it is. So it is similar to this kind of thing in one dimension. So in math, when you do integral u dv, you know it's u times v with the limits minus v du, right? Or in 3D, you can look at your textbook equation 1.59, and it's given in this format. It's going to be in a volume, if you have a scalar, and then you have divergence of some other vector integrating over d tau, that is equal to, first of all, you have these two at the boundary. So you have the boundary that gives you d tau are the closed surface, right? So you think of the balloon, it's the outer rim of the balloon. So you have F times A, dA, take the value of the boundary, F times A, so there is no dot, it's just multiplication because F is a scalar, and minus A dF, so D becomes gradient. Okay, so because this is the 3D, d tau. You see, it's really similar to this. Okay, so I'm going to use this equation to help me further simplify and expand this term, because I have the same kind of format, right? I have a scalar here and I have divergence of a vector. So I'm going to use this equation. So this work for this whole system has become, first of all, is the value of potential and E at the boundary surface. And then you have this volume integration of E times the gradient of V d tau. The first term, okay, so the second term is, here we're generating a very generic general formula, and we're looking at, okay, what is the system, what is the energy stored in all space? So if we're looking at all space, sorry, let me add another, let me put this page down here. The volume is all space. So you can see the boundary for the all space is at infinity far away. So the boundary is at infinity. So potential at infinity has to be 0. Electric field at infinity has to be 0. No matter what your charge distribution looks like, but of course they are for local charges, meaning that your charge is not infinite. You're not gonna have some infinite sheet or infinite rod. Those are not local charges, but anything else, they has to die away at infinity. That's only physical. So for those charges at the boundary, these terms are 0. So you're left with just the second term. So your system, energy of the system for a continuous charge distribution becomes this. You can see it's E times, again, negative delta V is E again, right? This is also plus a negative sign is also E. So you get E squared, E times E. So you get E squared, positive. Okay, so I have at this point derived another formula for a continuous charge distribution. You can see you only care about the E field because the energy is stored in the E field. So we have our first expression. Where is that? The first expression is here for a many point charges. The second expression is here, is using the E. You probably have already noticed some inconsistency between these two. And this is our next question. The inconsistency of these two are, the second one is always positive because E squared is always positive. The first one obviously can be negative, right? You can have a negative charge or you can have a negative potential. So how come these two are inconsistent with one another? Did we make a mistake in the derivation or what is going on? So I want you to, again, discuss this in your breakout rooms. If you have done reading, you probably already know the answer. But if you haven't, you can do more discussion. So take a screenshot and take a couple minutes on this question, okay? Okay, all right, seems like do I have any last minute vote? Okay, now let's take a look at this together. This is your results from the voting. Okay, so we have a majority answer voting for B, and there are some voting for C and D as well. So it looks like in the derivation, it seems like every step is okay, right? Every step is correct. But how come we end up with two different expressions? The first one indeed can be negative. So because there is possible to have a negative potential energy, it is possible. So it can have a negative quantity. But the second one for sure seems to be always larger than 0. And I just wanted to ask you what you think. Now, in your answer, if you can share with us, where do you think we have introduced a difference in our derivation so that we have changed the meaning of these two different terms? It seems like in the derivation, every step makes sense, but they end up to be indeed describing two different things. So where in our derivation do you think I introduced this sort of mistake? I'm gonna go back to the derivation so we can see. Where do you think that might have occurred?
It's somewhere where you begin your derivation. I know the discrepancy lies between bringing individual charges in and building an equation from that versus calculating the divergence.
Where it comes in here? Do you mean in here?
No, I'm just saying it's how you begin. I mean, I'm guessing, of course, but what I think is that it's how you began building your summation versus your integral.
Yes, it indeed happened from here to here. You're right. So even though it's subtle, you can see that when I making these two charges, when I make the charges individual, I'm very careful in emphasizing this V is a location of this charge, but not including the charge itself. It is due to all the other points where J is not equal to I. So somehow that writing went away. J does not equal to I. However, when you make it into a smear and you do a integration, sort of that boundary disappeared, that the V is simply the potential is due to the charge distribution, right? It's hard to separate this potential is due to yourself or due to some other charges. It's all in the same integral. So the location of R including itself. That's why there is a discrepancy in terms of the meaning of these two terms. The first term is the energy required to assemble the charges. The second term not only include the energy required to put these charges together, but also the energy to make the charges, because you're including the charge itself. And the second term is this, has included energy to make the charges. And Griffiths talked about a little bit difficulty or embarrassment with the classical and A&M theory is the sort of the idea of point charge model, right? Because if you integrate this over all space for a point charge, you will realize you actually got infinity. You have an infinite, you need infinite amount of energy to make a point charge. That doesn't seem physical. That he said we will continue to talk more about it in the later chapters, but I think the idea is has to do with the model of the point charge. If you jam everything into a point, is one point. Of course, you are looking at infinite charge density. You're also looking at infinite energies. In real life, we're not really looking at single point. Even your electrons has a fact size. So that's a totally different discussion. But I just want to say that the second term includes energy to make these charges, and there is some difficulty associated with our EM theory when we are talking about particular a point charge model. So going back to this question, the answer is B, okay, because the second expression also included energy required to make the charges, and the first is only the energy to assemble the charges. That's why there's some difference in there. The work we have done is by introducing the idea of the work. You can do positive work on it, you can do the negative work on it. And if you do positive work on the system will increase its energy. If you do negative work on it, the system will decrease its energy. So let's further just run with that thought and take a look at a couple more questions. So here is really just a two charge distribution, a positive Q and negative Q, and we are slowly moved together. So make sure that you emphasize the word slowly, that implied something. So how does the potential energy of the system change?
Does it remain constant?
Slowly meaning that you're not simply let go and let them sort of run toward each other. They're moving with a constant velocity, yes. Yes. Okay, there are two different reasons you can come up with to get the answer. So let's see what kind of reasons we can gather from you guys, okay? Again, just a couple minutes on this question.
Dr. Ryan?
Yeah?
Do you mind allowing us to share our screens?
Oh, I believe that I do allow that. Do I not? Let me see how. Go ahead. I'm going to try to figure it out, okay?
Okay.
Okay, any last minute vote? Okay, I'm gonna go ahead and end this. Let's take a look at our results. This is the result. We're kind of equally divided between increasing or decreasing. So what is the idea that you used to figure this out? Anybody tell us one method?
We use the potential energy equation.
Okay.
So KQ squared over R.
Okay.
As R gets smaller, the potential energy increases.
Wow, okay, so this comes from K Q1, Q2 over R. So in this case, one of them is a negative charge, right? It's negative Q, the other is another positive Q. So I do get KQ squared over R, but we should have a negative number, a negative sign. Yes, as R decreasing, this term increase, but you have a negative sign. So they overall should decrease, right? So this is just the charge of a particular, the total amount of charges. If Q1 is negative, you have to put negative sign. So that's one method. Is there another method by looking at the work done?
If they're moving slowly towards the center, that means something is, they're not accelerating towards each other, so some force is acting on them.
Ah, okay, so the force for the negative charge should be pointing to the left or right?
To the left.
The left. This is a force external. Yes, it is conquering the Coulomb force. Yes, and your displacement, you can see displacement is dl is to the right. Force dot into displacement, they're opposite signs. So you have done negative work, which means you have decreased the energy of the system. So they get the same answer. So B is correct. Right. All right, so that's all for today. If I don't see you in our office hours, then I'll see you on Friday at our recitation. Okay. All right. Have a good rest of the week.
Thank you, Dr. Ryan. I'll see you in your office hours.
Okay, sounds good.
Thank you.
Thank you, everyone. Have a good day.